Hi, in this video, we're going to talk about how things fall. So I've got a 5-pound dumbbell here, and I've got a 20-pound dumbbell here, and I want to see how these two objects compare whenever I drop them. But I'm going to drop them from a little bit taller of a height. I've got my ladder here, so I'm going to get up to about a height of 6 feet or so. All right, I'm going to hold out the two weights, and I'm going to try to make sure that they are at the same starting height. So I'm going to hold them out like this. I'm going to drop them. And what do you think will happen? Which one will hit the ground first? All right, let's try it. Okay, let me try it this way. Okay, same height. 3, 2, 1, drop. Look at that. They hit the ground at the same time. A bit unexpected at first. Maybe you've heard this before, but why is it that they hit the ground at the same time? Isn't it true that the 20-pound weight is heavier than the 5-pound weight? Of course that's true, right? Gravity is pulling this one down with more force, and usually with more force, you get more acceleration. They both start speeding up at the same rate, though, and they both hit the ground at the same time. So why is that? The main answer is because even though this one has 4 times as much force pulling on it than the 5-pound weight, it also has 4 times as much inertia, 4 times as much mass. So it's really hard to get it accelerating quickly. And so even though you're pulling it further down faster, it's got more mass, more inertia, so it doesn't really want to move as much. So it has 4 times as much force, but also 4 times as much resistance to the force. So they end up having exactly the same acceleration as a result. Now, this is true for objects that are not affected by air resistance, but there are some objects that have more of an effect due to air resistance. I've got a grocery bag here, a Walmart bag, and I've also got a wrench. So let's try dropping, oh, the wrench is stuck in my pocket. Okay, let's try dropping these two and see what happens. I'm sure you can make a pretty educated guess about what's going to happen here. But let's just test it out. That's what science is all about, testing out different ideas. So dropping them in 3, 2, 1. Okay, yes. The wrench hits the ground first. Okay, but I thought I just said that 2 different weight objects can hit the ground at the same time. And the reason is obviously because of air resistance. Because there's air in the way, this lightweight bag is really affected by air. This wrench, not so much. And so the Galileo first made a prediction saying that if you were to somehow remove the air from the Earth, then technically the bag and the wrench should fall at the same rate, because just like the 5-pound weight and the 20-pound weight, even though the wrench is much heavier, I had the wrench in this hand, even though the wrench is much heavier and the bag is much lighter, the wrench also has more mass and resistance to movement and inertia than the wrench does, and so than the bag does, and so they both should end up accelerating at the same rate. So let's look at this a little bit more closely. So if air resistance is removed, or it's small enough that it can be ignored, that is negligible, all objects, regardless of their mass, fall at the same rate. This idea is called free fall, and free fall is defined as moving only under the influence of gravity. So that's no air resistance or any other forces acting on it, just gravity, an object falling. But free fall actually includes objects moving up as well, and down and sideways. Just as long as it's only gravity that's acting on the ball, you've let go of it and now it's freely moving or falling. So, by how much do objects speed up in free fall? So you drop an object, how much speed does it gain each second? We've measured this many times over the years, and so this number is pretty well documented at this point. It's very certain. And it comes from this ratio of weight to mass that we've seen before. So a bigger object has a higher weight, right? Let's say we have the big dumbbell here, 20 kilograms for its mass, but that also means it has a higher weight. So it's being pulled down by gravity very strongly, but it also has a lot of resistance to accelerating because of its mass. And so that ratio of weight to mass is 9.81 meters per second squared. This value is the acceleration due to gravity. It's how quickly an object speeds up. But that ratio of weight to mass is the same for a smaller dumbbell, as we saw for the 5 kilogram mass in this case. The weight is 49 newtons, but you do that same division, 49 divided by 5, you also get 9.81 meters per second squared. So it doesn't matter what your weight or mass is, it always ends up being the same acceleration on Earth if you ignore all other factors. So 9.81 is a number that you'll see a lot in physics. Let's look at an example of an object that's been dropped from a tall cliff. So you drop an object, it starts falling and speeding up, getting faster and faster. When you first drop it, it's not moving at all. After 1 second of falling, it's moving at negative 9.81 meters per second. I've also included the rounded numbers over here just so it's simple, because a lot of times you'll just round up this 9.81, you'll round it up to 10, and so then it's easier to follow. That as it keeps falling, it continues to gain speed by 9.81 or 10 meters per second each second. Notice I do have a negative sign in these numbers because it's a vector. This velocity is a vector and it's moving down. If you drop an object, it moves down towards the Earth. So it gains negative 9.81 meters per second velocity each second. We can write that as, like, mathematically as a symbol here with little g. So little g represents the acceleration due to gravity, and there it is, 9.81 meters per second squared. Now this applies not just to falling objects that are moving down, but also objects that have been thrown up into the air. So take a look at this this graphic here. It's really helpful to take it all in and visualize what's going on here. So an object is thrown upwards at a speed of 40 meters per second, and I've rounded these numbers for simplicity. After 1 second of moving up, it starts slowing down, right? You throw something up in the air, it doesn't stay at that same speed, but it starts slowing down because gravity is pulling it and working against it. It's going up, but gravity is trying to slow it down. And so after 1 second, it's going at 30 meters per second. After 2 seconds, it's slowed down by another 10, so it's now at 20. 3 seconds is at 10, and then at 4 seconds, it's reached zero velocity. And so at the very top of its trajectory, an object actually pauses and stops for an instant before it turns around and starts falling back down. So the instantaneous speed at the top of your trajectory here is 0, just for a moment, because after that, gravity is still working on it, pulling it down, and so it starts to speed up, and it goes downward at 10 meters per second. Another second passes, it's at 20, then 30, 40, and if we kept going, it'd be going at 50, and that pattern continues on and on. As long as air resistance can be ignored. So the change in velocity is the same whether the ball is going up or down. It's always negative 10 meters per second squared. That's what's happening each second. You have 10 meters per second of change, always directed towards the downward direction. So that's all I've got for you in this video. Remember, everything you have is a gift.